Hello and welcome to my fourth video in my video series for topology. I'm Jose Osa, and today we'll be discussing a problem that involves door spaces since it's related to my talk as my final project. So here we're going to deal with this problem set from section 1.3. It's problem 1.3.9 from section 1.3, which just deals with different types of topological spaces. And today's problem just asks us to be able to determine certain things about door spaces. So first off, we start with the definition of a door space, that a topological space is said to be a door space if every subset of X is either an open set or a closed set or both. It doesn't mean that all of them have to be the same things. It means that some sets can be open or some sets can be closed, or the sets can be both open and closed, meaning clopen. Now, it doesn't mean that if something is not closed or not open, it's a door space, because it is not. It just means that a set has to be open, closed, or both, and a set existing within the topological space. So we're going to work with our definitions of discrete space and indiscrete space to solve the first two questions. And the first question asks us, is a discrete space a door space? We have to remember that by definition, a discrete space is one in which every set is both open and closed. And it can be either in a, this is just how it looks in a Euclidean topology, but just to get my point across, a discrete space has no clopen sets. It has sets that are either open or closed. Every set is open and closed, meaning that they're all clopen spaces. I just got confused with indiscrete space. My apologies. A discrete space is in which every set is both open and closed, making them clopen. But they are defined. They are open and they are closed. They are not open or not closed. And since one of the possibilities in our definition from a door space is that all sets are either open, closed, or both, it is satisfied that all the sets are both. So we have that our first question is a door space. Now for the second question, we have to work with the definition of a discrete space, which is defined as a space in which all subsets of X except X and the empty set itself are neither open nor closed. Now here, going back to what I emphasized in the beginning, this does not satisfy our definition of a door space because the sets have to be open, closed, or both. They cannot be neither. So just by definition, an indiscrete space would not be a door space, making our second question not a door space. Now we want to deal with our third question, which tells us that X is an infinite set and tau is a finite closed topology. This means that all sets that are open have to be infinite and all the sets that are closed have to be finite. An example of a set that would not satisfy this under the Euclidean topology, for example, would be the odd or even numbers, since their complement is infinite as well. So both would be open, but they can't both be open because one is the complement of the other, so they're just not defined. So those would be an example of something that not. So this means that all the finite sets are closed and their complements are infinite, like I said. So this means that there are some clopen subsets, such as, again, the even and odd integers, that do not satisfy this definition. However, the definition of the finite closed topology implies that some sets are strictly closed and some are strictly open. Thus, since some sets in this topology are neither open nor closed, like, again, the odd or even numbers, this space is not a door space, because our definition of a door space requires that every set is either open, closed, or both. It cannot be neither. Again, this thus making our third question not be a door space. Now, our fourth question is mostly about us finding what the subsets would look like. So we have the X set that is that has A, B, C, and D in it as elements. So we have to find the topologies on this set that make it into a door space. So if we're working through this one, for example, let's get our first topology. We quickly see that first, in order for something to be a topology, we always have to have the set itself, the empty set, and elements from our set as subsets and the unions of set elements. So for example, if we had the subset just containing A within this topology, then that would mean that the complement of A is a set containing B, C, and D, which, since it's not included in the topology, we see that this set is closed because it's not in the topology. And the union of A with itself gives us A itself. So this means that all the sets in the topology here are closed or open. But yes, no. So this topology would be including into the door space because the complement of A is this set, which is a subset of X, which is closed in this topology because it's not included in the topology. And now, if we want to think, this works for any element that we have in this topology. So it works for B, it works for C, and it works for D. Now, the more interesting questions are, how does it work with our, if our topology includes more things than it? Let's check it out. So let's say we have a topology that includes A and B, for example. We have X, we have the empty set, we have A, and we have B here. Then the topology has to include the union of them, which I already wrote here, just sort of intuitively, because that's how topologies have to be. So here we see that we have these two things in the topology and the union of them. And if we think about how the complement of this, of everything that's in here looks like, we see that the complement of AB is the complement of AB. Here, let me write it. Would be D and C, which are not included in this topology. So meaning that they would be closed. Then we also see that the complement of any of these single elements, say A complement, would be B, C, and D, which is also not included in this topology, meaning that it's closed. So this satisfies the door space property. So similarly, we can think of all the pairs and having the single elements of the pairs. We have the empty set, we have B and C, and we have B by itself, and we have C by itself. They all satisfy the same properties, all the topologies with the pairs. So now we have A and C. And now let's think about how the topologies containing a set with 3 elements in them look like. So if we have, say, A, B, and C, we also have A, B, and C because we need the union of them, in which we will see that the complement of A, B, and C is D, which is close in this topology since it's not included in the topology. We also see that the complement of any individual element is similar to this one. Well, actually not similar, it's the same as this one. And complement, I'm sorry. And then it applies the same way to the other topology. So I'm going to write here the topology without A, and then the topology without B, and then the topology without C, sorry. So those all would work under this. And then now we only have one more topology, which is the topology that includes all the elements in the set. B, C, D. Oh, sorry. Before I move on to this one, in this topology, I forgot to write the individual unions of the sets, which would look like we have like the set of A and B, then we will have the set of B and C, and then we would have the set of A and C. But similarly, we see that the complement of AB, for example, is C and D, which is not included in this topology and would mean that C and D is closed. So we still have all of our sets that exist in this, that are created by every subset of X is defined as either open or closed, satisfying the door space topology. Now going back to our final topology, we have this and we have the union of all of them, which is just equal to the set itself. This is all equal to X. And then we see that all of the unions of our sets, for example, set A, B, and C, its complement would be just D, which is also open in this topology. So now we have arrived at something that doesn't quite work under our door space topology definition, because every complement of every subset that you can think of is also included in this topology, meaning that this last topology that includes everything would not be a door space. Every topology other than that, including our elements, would be therefore a door space topology. So as a total, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. We have a total of 11 topologies that are door spaces with this particular X. And that is the last question of our problem. And thanks for watching.